Welcome to the video lecture on quantum mechanics, the most important component of quantum mechanics being the Schrödinger wave function. Presented by Dr. L. Cinderella, Professor of Chemistry, National Institute of Technology, Trichy. Schrödinger wave function is very important in defining the wave characteristic of subatomic particles. We'll see about some of the cases in which finding the exact solution of Schrödinger wave function is possible. If you look at the instances in which we are able to have the complete solution for Schrödinger wave function, it is the cases wherein we are able to restrict the number of electrons to be 1. Hence, some of the simple systems can be particle in a one-dimensional box, particle in two-dimensional box, and particle in a three-dimensional box. Simple harmonic oscillator similar to a pendulum, rigid rotor similar to a hard ball even after hitting any surface without showing any change in its spherical structure, and ultimately hydrogen atom wherein we are able to have just one electron. Particle in a one-dimensional box. Here in this presentation we will not be concentrating on the equations, we will only concentrate on the physical meaning of each of the cases that have been listed in the earlier slide. Particle in a one-dimensional box embodies the translation energy of a molecule or a particle which have been bound with certain boundary conditions. A typical example in chemistry is a conjugated system wherein we have the pi electron which are delocalized. The pi electron is able to move from one position to other position, and hence it is said to be delocalized, but without escaping away from the molecule. That's the reason why it is said to be satisfying the boundary conditions. So here the energy of this particular system is obtained based on the complete solution of Schrödinger equation. We'll see about the details of all the equations, solutions, and the importance of each of the form of solution in one of the coming presentations. The next one is a particle in a three-dimensional box which defines the energy of a molecule as a function of its three coordinate axes, and in this case the property that we get is the degeneracy of states, which are basically nothing but sets of quantum numbers which give rise to different energies with the same different energy states but with the same energy, and those energy states are known as degenerate states. Next example is a simple harmonic oscillator. Simple harmonic oscillator is a picturization of a setup wherein the potential energy of the oscillator keeps on changing as a function of its position. The potential energy diagram of a simple harmonic oscillator is a perfect parabola as defined by Hooke's law. The shape and the steepness of the parabola define the rigidity of the bond between two atoms, which give rise to or which behave like a harmonic oscillator. The next example is a hydrogen atom. This is the smallest three-dimensional system that is able to show the combined characteristics of three variables, namely length, radial function, and angular functions. Radial function and angular function could be defined as polar coordinate functions. These are the examples. For the solutions that are obtained from the Schrödinger equation. And if you look at the mathematical expression of Schrödinger equation or solution of Schrödinger equation for each of the examples that have been listed now, we'll be able to derive very significant interpretations that will convey to us the energy, whether it is in the form of kinetic energy within the bound state, or translation energy within the bound state, rotational energy or vibrational energy, or all of them together. In the case of a rigid rotor, which stands for a diatomic molecule that rotates about an axis, this axis will be perpendicular to the internuclear axis and also passes through the center of gravity of the molecule. In this case, the total energy is the kinetic energy. All these are the systems which give rise to which could be the solution of these systems could be obtained exactly by solving the Schrödinger equation for the systems.